Hello.
Good afternoon, sir.
Good afternoon, madam. Can you hear me?
Yes, sir. Yes, sir. Sir, we shall make a try for our presentation, sir. You please share a screen, sir. Let us test it. Live.
Kavita, madam, can you hear me now?
Yes, sir. Yes, sir. We can hear you, sir.
Okay, so let me share.
Yes, sir. Yes, sir.
It's telling me I can't share your screen. So maybe you can give me a permission.
Sir, please.
I'm not able to share. It is showing that it's needed permission from your side. So maybe I think it's a Google Meet, right? So I think you have to make me a host or maybe co-host, so I can able to share my.
Okay. Meeting host. Sir, already you are in a host, sir.
You must grant permission in order to share your screen. Select Safari setting for this website. Update permission. Oh, I think my web browser, I think it's not allowing. Let me. Okay, give me some minute.
Yes, sir. Yes, sir. Yes, sir.
தெரியுதா? தெரியும் தெரியும்.
Good afternoon, Anandrath sir.
Good afternoon, madam.
Good afternoon, madam. Yes, sir. How are you, sir?
I'm good, thank you. How are you?
Thank you. How are you? Fine, sir. நீங்க வரதுக்குள்ள மெட்ராஸ் எல்லாம் மழை பெய்ஞ்சு முடிச்சிருச்சு.
ஆமா ஆமா.
நீங்க அதுக்கு முன்னாடி வந்துட்டீங்களா இல்ல அப்புறம் வந்தீங்களா சார்?
இல்ல அது முடிஞ்ச அப்புறம் தான் வந்தேன். அந்த புயலோட கொடூரங்கள் முடிஞ்ச அப்புறம் தான் வந்தேன்.
ஓகே சார், ஓகே சார். நாளைக்கு இதே டைம்ல ஸ்டார்ட் பண்ணிக்கலாம் சார்.
ஓகே
ஓகேங்க சார், தேங்க்ஸ்.
Madam, can you able to see my screen now?
Yes, sir. Yes, sir. Yes, sir. We can see your screen. Yes, sir.
Sorry, I tried all the way about that. So finally, I download and okay. Anyway, so can you see my presentation now?
No, sir. No, sir. Your Google Meet screen is visible, sir.
Now?
No, sir. No, sir. You can see your Google Meet screen alone, sir. Not the presentation.
Share the entire.
Yes, sir. While sharing your presentation, you have to give that window, sir. Sharing.
That I am. sharing it, and I am opening my present.
You have to select the window, sir. Next window. PPT, presentation window.
Now, can you see?
No, sir. Your Google Meet only is visible.
क्या open करते हो? Explore कौन सा?
அதில் வச்சு work பண்ணி. Sir, now I will share for. I'm sharing, sir.
Yeah, I am sharing, but you are not able to see.
No, sir. No, sir. Sir, while sharing, you will have that Chrome tab, window, entire screen. So you have to go that window, sir.
Pradeep, stop sharing it now. Then you try sharing it again. When you do that, there will be a pop-up window in which you should choose entire screen, not the tab.
I'm sharing that, stopping and sharing again.
You can stop sharing. Stop the sharing now. Yeah, now try again.
Sir. ஷேர் பண்ணாதான் தெரியும் இல்லையா?
நீங்கள் லாகின் பண்ணுங்க இல்லாட்டியாங்க. இதே ஐடியில் நீங்கள் அங்கே போய் ஓப்பன் பண்ணிக்கிங்க, வருதான்னு பார்ப்போம். சரி ரைட், ஓகே.
Can you hear me now?
Yes, sir.
Okay, let me share it.
Yes, sir. Now it is visible.
Is it visible now?
Yes, sir.
Oh, okay. Sorry, I think my camera is not working because I use computer now and laptop. That was a difficulty, so I was unable to share the screen. Maybe that is notebook. Anyway, so now it's visible, right?
Yes, sir. Sir, please move it to slideshow, sir. Slideshow.
Yeah, I will move it. I'm just checking it. It's okay. I will handle it. Yeah. So is it in slideshow mode now?
Yes, sir.
Okay. Thank you. So shall I start or?
Yes, sir. Sir, first, just a minute, sir. We welcome you. Formal welcome.
Okay, thank you.
Good afternoon to all. I welcome you all for the third day FDP on Development of Materials, Characterization Techniques and Their Future Prospects, conducted by the Department of Physics under DBT Star Status Scheme, Sri GVG Visalakshi College for Women. Today's session on Exploring Nanomaterials by High-resolution Transmission Electron Microscopy will be handled by Dr. Pradeep Sarvade. I am happy to introduce today's resource person, Dr. Pradeep. Dr. Pradeep is Assistant Professor in the Department of Physics at University of Mumbai. He is a recognized PhD guide at Department of Physics, Center for Nanosciences and Nanotechnology, and Department of Chemistry since 2015. He already supervised 5 PhD and 4 MPhil and more than 50 MSc project students. Currently, 4 PhD and 1 MPhil students are pursuing their research work under his guidance. He was awarded the gold medal for best doctoral thesis from Hanyang University, South Korea. He developed a convenient synthetic protocol for the millimeter and micrometer sized hydrophobic and hydrophilic nanoporous silica aerogel beads with 3D nanostructures under ambient conditions during his postdoctoral research at Hanyang University. He has published more than 90 research articles and 3 Indian patents with a total impact factor of more than 400, H-index 29 and more than 2000 citations. In high-impact journals such as Chemistry of Materials, Chemsyscom, ACS Sustainable Chemistry and Engineering, and Chemical Engineering Journal, Journal of Material Chemistry, etc., including a book on silica aerogels. He has given more than 30 invited talks at international and national conferences and various colleges as well. Behalf of the organizing committee, I offer a warm welcome to the resource person. I extend my hearty welcome to all the participants from various institutions. Once again, I welcome you all for today's session. And now the session is over to you, sir.
Okay, thank you, madam, for introducing me. I hope you all the participant can hear me clearly. If anything in between my presentation, you can ask me questions you can unmute yourself. Okay, so before I just go for the talk, I apologize for the connections. Also, I would like to take this opportunity to thank Dr. Kavita, madam, inviting me to deliver talk of this FDP online program. And rest of the staff members who have put the hand together to make this event online. Hello. Hi, yes, madam. Can you hear me?
Yes, sir. Yes, sir. Thank you, sir. Thank you,
Okay,
sir.
okay, sure. So I think this FDP course is started maybe 2-3 backs, I guess. So all the participants, I think you might have heard a lot of presentations from the various speakers. I guess you might have heard some of the characterization techniques. So even though it is online and some of the slides, because the online always get difficulty and some of the slides maybe move fast. So even though if you are in expert in the techniques such as TM or SEM, maybe you, because I always say that, okay, we cannot get all the things from the presentations. Maybe you can try to get something. So I will like to give some flavors from these techniques. So I hope if you able to get something from this my presentation, that will be good. All right. So here, maybe how much time? 45 minutes or 1 hour, madam?
Sir, 45 minutes presentation, sir. Last 15 minutes for interaction, sir.
Okay. So it's already maybe due to the connection is spent the time. So no issues. So next 5 minutes, maybe I will take you to some of the important parameters of some electron microscope. I will touch upon some scanning electron microscope and then show some result and some elaborate how to elaborate the result and the transmission electron microscope. Basic, or maybe I will, if we get the more time, I will go for the high resolution transmission microscope in details. Okay, so well, so my topic titles you can see: exploring the nano object with the electron microscope. Okay, as we see, this is the nano worlds. Okay, so the things which is very smaller we cannot see by our naked eyes, because these are the very smaller and our eyes have limitations, right? So outline of my talk will be some the introduction. I will give some of the materials, modern materials, and the importance of the nanomaterials. And these nanomaterials using some characterization techniques, because we want to know the features of these nanomaterials and which are the characterized techniques, and among them electron microscope, which is a very important tools to see the small object, okay, micron or nano object. So I will talk about the history, some working principle of the SEM applications, then TM, history of the TM, then imaging modes of TM and HRTM. Then additional features of the HRTM, that is yields, it's similar to the EDX, and then application, and then I will conclude my talk. Okay, so before I go in the electron microscope, I wanted to get you in the history materials, because the techniques, electron microscope techniques is mostly used in the nanomaterials and nanoscience technology. See, nano object, right? So if you see the materials in the history, humankind started to use the stone, copper, and bronze, and then Iron Age is much started late. It is believed because of the high temperature, right? And after the discovery of the several elements, among them the oxygen, silicon is the most abundant element on the earth. And more combination of the elements, we are the researchers or human beings started to make new materials, and this is a new era of the modern nanomaterials. And this nanomaterials, you can see it has various applications in various field, right? For example, you can say it's automobile industries, electrical, cosmetic industry, agriculture, pharmaceutical industry, textile industry. So all this, the element of the from the periodic tables, combination, permutation, we make a new materials, and it has a various applications. So coming back to the nanomaterials, we normally say it's the length scale 1 to 100 nanometer. The nanometer scale we called as the nanomaterials. Now there are four types of the mainly nanomaterials we consider: 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensionals. So 0-dimensional, good example you can say fullerene. 1-dimensional good example is graphene. 2-dimensional nanowires, nanotube, nanoparticle. These are the smaller object, right? So if I have to see, we have to use some of the tools. Now let's spend some few minutes to what is a nano, to understand what is nano, even though you know it, but we always talk nano is 10 raised to minus 9, even though it is just numbers, right? And suppose if we have to visualize, or if we have to understand how small is 1 nanometer, how small is 1 nanometer. Now, if you think in front of your eyes, can you able to think or visualize that is how, or 1 nanometer, the scale? Because we are not able to see, right? So for that, maybe I can just explain you simply way. We can think comparatively to the size of one atom, the size of the nucleus. Size of one atom is 10 raised to minus 10. Size of the one nucleus is 10 raised to minus 15 meter, right? So considering the atom and molecule, or can you think of the nucleus compared to the atom? Maybe, okay, let's see how we can make it simple. So size of one atom, as I said, 10 raised to minus. If we multiply the same number, put the same side, it will remain the same because it's assuming is a constant. So multiply by 10 raised to 3 for both sides. What do you get? 10 raised to minus 10 into 10 raised to 13, you get 10 raised to 3 meter. 10 raised to 3 meter is nothing but 1 kilometer. Now we can assume 1 kilometer, right? The size of nucleus, if you multiply the same number, you get 10 raised to minus 2 meter. Now 10 raised to minus 2 meter is nothing but 1 centimeter. Now you can assume 1 centimeter and 1 kilometer, right? The respective distance, what we see. And we know that what we believe more, what we see, right, by our eyes. So now you can visualize nucleus size and atom size with considering 1 kilometer and 1 centimeter. You can make a 1 kilometer diameter, take it and make it circle, right? So that may be atom, and you can, the green piece, we eat it, that is roughly size around 1 centimeter, isn't it? So maybe you can put it in center. So you can assume that is the size of atom, or compared to 1 centimeter and 1 kilometer diameter. Now, 1 nanometer is 10 raised to 9, 1 billionth of meter. So now you can visualize how 1 nanometer is, how small it is. Or maybe another way you can compare with the earth, basketball, and nanoparticle. If you assume the nanoparticle is a 4.9 nanometer, you have to divide it 51 million times then one will be a 5 nanometer scale of that nanoparticle. So you can consider that. So what if we divide this bigger object in smaller, what we get it, or what we can do, what we can change? For example, properties, right? Property means different properties. For example, surface area. Now if you take a one block and you did it in 2, 4, 8, 16, 32, so the surface area increases, means increase the ratio of surface to volume ratio, right? So this is the one of the important properties you can change, reducing the size. Another one is optical properties. Optical properties means, for example, you can say gold, bulk gold. It looks in a golden color, isn't it? If you make a nanoparticle of gold, it's look in, or it's appear in ruby red color. Now see, elements are same, right? But we are just reducing the size. Means reducing size. What we see, different color. Different colors means optical properties. Okay, we tune, or we can change the optical properties, reducing the size. Similarly, this effect can be observed in the silver nanoparticle. Another important thing, parameter properties, electrical properties, band gap. Okay, changing the size, band gap, you can change this. That band gap is nothing but electrical properties. Okay, so these are the three main properties, very important for the nanomaterials, and using this property, you can use that nanomaterials for the various application. Now, among this, some of the properties, how you can identify, you have to how to identify, then you use tools. I mean, we use the tools, right? So that is called as a characterization technique. There are different kind of characterization techniques, depends on the what properties you are looking for that. So I will not go for it. Here I'm going the morphological properties, size and shape, because these object, nanomaterials, nanoparticles are very small. We are not able to see by naked eyes. So therefore we can able to see, or we need a different aids or tools to see that object. So scanning electron microscope or transmission electron microscope is a important tools or versatile tool to see the nano object. Okay. Now, let's talk about the resolution of the human eyes. Can anybody tell me the resolution of the human eye? How small object that we can able to see by naked eyes? Anyone? Okay. Now see the butterfly, right? But the detailed structure of the butterfly on the wings, if you have to see, we cannot see by the naked eye, because this texture of the butterfly, it's in micron size, isn't it? Or maybe you think about the hair. Okay, you can think of the one single hair. Single hair, it is size around 80 to 120 micrometer, right? So if you take one single hair and if you cut it in the exactly half, assuming it's 80 micron, then it will be 40 micron. So half of the hair, can we see? Assume you can take one single hair and then you cut it in half, exactly half, and then can you able to see the single that half? Horizontally, I'm talking, telling that cut the hair, human hair. Maybe you suppose someone have a good eyesight, maybe we can see 40. So it's 40. Now that's half. We further divided in two pieces, exactly two pieces. So one will be a 20 micron, right? So can we able to see that half, 1/4 of the hair? Maybe some of, right? Or may not. If you divide it further, maybe it will become as a 10 micron. So may not possible to see. So maybe below 20 micron, it is difficult to see by naked eyes, right? So you can say human eyes resolution is 0.2 mm apart. Okay, means we distinguish the two objects which is apart from 0.2 mm. Now I purposely put this image. What is this? This is a human here, right? Now see, these are the picture taken on the optical microscope. Okay, now if we touch our hair, it always look like a smooth, right? We don't feel these textures or maybe this how can I say, roughness on the hair. Obviously it depends on the what kind of the soap shampoo you use. Your roughness of the hair will be different, isn't it? So the means our open eyes to see the point which is even closer than 0.2 micron. It is very difficult. So for that, or maybe we can say, okay, so to see the object which is smaller than 20 micrometer or 10 micrometer, you need a lenses or maybe the tools, right? So, or you can say, I put it, suppose now this rose and lips are there. So the fly sitting on the lips, in first image you are not able to see. Now you zoom it with the some DSL camera or something like that, you are able to see. Now you want to see detailed structure of the eyes, you have to zoom it further or use high resolution camera or lenses, you can able to see. Now further eyes which has a beautiful texture of this fly, it has it's look like a honeycomb structure, and also it has some tissue antennas which may be actually able to see that bird fly, sorry, yes, fly. So these tissues or this something is made of some nothing but biomolecules. Okay, so RNA or DNA, suppose it is the length scale of the 10 nanometer, you are not able to see because this is biomolecules which is very small. So nanoscale nanomaterials, if you have to see, you need a special kind of the tools. Okay, so we talk about the limitations of the human eyes. Now let's come to the main point. Okay, so you need a tools. Now human in the 17th, hello, is anyone talking? Do you hear me?
Yes, sir.
Okay, so let's talk about the history of the microscope. Why microscope is developed? Because some smaller object we are not able to see. Actually microscope, this word is derived from Greek word, Greek micron. Micron means small, and scopio means look at. So initially light microscope is developed at the 17th century by Galilean telescope. That then after that Dutchman Antony who developed the simple microscope, that is single convex lens. Then after this compound microscope is introduced with the combination of objective lens, eyepiece and mirror. Okay, now using this compound microscope you are able to see more smaller object. Okay, now that is a light microscope, you can say that. Okay, so resolution of the light microscope is little more than naked eyes, because here use some optical lenses and mirror. Okay, now this microscope, or you can say using a best possible lenses, or before that German scientist Ernst Abbe in 1873 he introduced the equation relation between the resolving power and the wavelength. Okay, now the light is wavelength, we know the visible 300 to 350 to 700. So D is equal to 0.61 lambda divided by n sin alpha. Now n sin alpha is nothing but numerical aperture of that microscope. So best possible numerical aperture you can use, light lowest wavelength of the light if you use, then you can able to get the resolution power of this compound microscope just under 200 nanometers. Okay, Now, if you have to see the object, because some of the nanoparticles are very smaller, bacteria and viruses, right? So you cannot use this microscope because the wavelength of light is visible light is below, I mean 350. So you cannot go below that. So you need different source of the light to see the object. Okay, so after the discovery, this J.J. Thomson and D. Broglie, he gave the equation for that lambda is equal to H divided by mv. Now, I hope there's some of the participate from physics. So this equation, H is Planck's constant, m is the mass of the object, v is the accelerating voltage. So depends on the accelerating voltage, the wavelength of the new source of the light maybe get a smaller, assuming as an electron. Okay, so suppose you apply 300 kV. Okay, you apply 300 kV, a Planck's constant and mass of the electron. So the wavelength of the electron wave, you get it 0.00 angstrom, 0.001 angstrom. So this wavelength of electron is very smaller compared to visible light, because visible light is in very large wavelength, right? So, and this electron beam is behave like a light, similar to the light in the vacuum, which is very and then it is also movement of the electron wave, it is also deflection of the electron wave, it also depends on the electrical and magnetic field. Means you can change the path of the electron beam by using a electrical and magnetic field. Okay, so now this is actually first microscope designed by Ernst and Ruska, University of Berlin, the TM. First TM is developed. Okay, then SEM is developed. Now the first electron microscope, which is used to two magnetic lenses. Okay, so now optical microscope is a optical lenses is used. Electron microscope, because electron source is there, so electromagnetic lenses are used. Electron magnetic lenses is nothing but it's a coil. Okay, so first transmission electron microscope, the resolution they achieved 100 nanometers, which is mean by twice as good as the light microscope. Light microscope we have seen 200 nanometers. So the best possible they observe initially the resolution 100 nanometer. Okay, and if we look the today's advanced electron microscope, the resolution you can get 0.5 nanometer, or which is actually 40,000 times better than our typical or compound microscope, and it is 4 lakh times better than the unaided eye, or you can say naked eyes. Okay, so we see the first use light as a source, and to see the smaller object because the wavelength limitations. Now electron is used as a illuminating source to see the smaller object. Now let's see types of the microscope. Okay, so optical microscope, which is use a light. Scanning probe microscope, which actually use a physical probe. Physical probe is nothing but sharp needle or wire it is used, or the filament to probe on this to your sample. And third one is called as a charge particle, or you can say electron or ion. Now scanning probe microscope is like a AFM, atomic force microscope. Okay, so that another kind of the microscope I am not going to talk about. The charge particle sorry, charge particle microscope, which actually use electron or ion. Okay, so that beam of charge particles or electromagnetic waves, and it uses electrostatic lenses altogether. All right, so why electron microscope need? Because as I said, it is a nanoparticles, if we have to see, which is very smaller, we are not able to see by human eyes, and the limitation of the light. We need a different source of the different source to illuminate the your object, which is actually I mean the wavelength should be a very smaller compared to the visible light. Okay. Now in the nature we see different morphology, right? Morphology and shape object, like if you just see the flowers you see different shape and different size. Okay, but this is in bigger size. Now nanomaterials, suppose you make it in the suppose nano flowers, like nano marigold flowers, suppose it is a size is less than 100 nanometer. Now in order to observe it or confirm their morphology, you need to see this object under the electron microscope, because nanorods, nanoparticles, these are the very smaller. You are not able to see by the optical microscope. And you know that the properties of nanomaterials you can tune, reducing the size and morphology. Okay, so most of the research is now moving around the nanoparticles and nanotechnology, right? So it is very important tools to see this morphological shape, sorry, morphology, that is shape and size. Okay, so you need microscope. Now I will talk about scanning electron microscope first, and then I will go for the transmission electron microscope. Now scanning electron microscope is nothing but using an electron beam, scan your sample, your required or raster area. Now the scanning electron microscope, the 4 important features you can find out observe using scanning electron microscope. One is a topography, another one is a morphology, composition, and crystallographic information. Okay, now topography is nothing but how your object or sample or texture it's look like. Okay, so that information you can get it of your nano sample or micron cell sample from using scanning electron microscope. Another one is a morphology, shape and size. Okay, what is the shape of the sample nano object, what is the size of your sample. Another one is that nano material or your nano object is made up of which element. That means the composition you can find out, or the information related to your composition of your nanomaterial, you can get that information using SEM. Lastly, you can find out the crystallographic information. Okay, means how your materials is arranged by atoms, whether it is arranged by regular patterns or irregular patterns. Okay, so that information you can get it from the SEM. So these 4 important information you can analysis of your nano object or nanomaterials. Okay, so it is very important tools. All right, so if we compare the light microscope and electron microscope, as I said, light microscope or light microscope and particularly scanning electron microscope. Light, where light use compound microscope, but scanning electron microscope, highly energetic electron beam is used. Okay, now if we talk about the magnification and resolution, the optical microscope resolution magnification you can get 1400 and the resolution is 0.2 mm. Okay, in SEM you get high magnification around 2 million and the resolution is very high, 0.5 nanometer. Okay, so you can see the small object, bacteria and viruses, but not using SEM. Only you can say some, how can I say, above 50 nanometer particles or object, if you can able to see SEM. Okay, SEM also has limitations because of the resolving power of SEM is compared to low, is low compared to transmission electron microscope, that we will go and discuss later on. All right. So to understand the SEM, I just wanted to to see the component. I don't know, or I hope you might have seen the some SEM microscope somewhere. If you not, this is the actual picture of the SEM microscope. This is a Nova Nano from FEI. So it has a, this is inside this schematic diagram. It has an electron gun, and then anode plate, then condenser and objective. So there are series of condenser or objective lenses and scanning coils, which actually scan your sample using highly energetic electron beam. Then you have detector, okay, and the specimen. Detector spacing above the specimen, which actually detect the signal from your sample. Okay, so let's see what are kind of the signals. So this the particular SEM Nova Nano, which actually consists or it has a EDX. Okay, so this is the EDX detector here. This is the electron column. Okay, and this is the chamber, sample chamber. Inside you have vacuum system, because you this analysis is done under the vacuum. Okay, so vacuum is very important. Why vacuum is important? Because electron beam travel in atmospheres, because the electron will collides on the gaseous molecules and it will lose the signals. Okay, so get good signal and good quality images, means correct images, you need to operate in the high vacuum. Okay, this vacuum is achieved by the some different types of the vacuum pumps. Okay, diffusion pumps and turbo pumps, molecular pumps. Okay, so let's talk about the principal element of the SEM. Okay, now the three main components of the SEM: electron column. This is the electron column, which contains the electron source, electromagnetic lenses, and aperture. Okay, the vacuum system. This is the vacuum systems, vacuum chambers, which holds the vacuum, and signal detections, which have the signal detectors. Okay, which collect the signals, and electronic, which produce the image from the signal, and this the signals is connected with the PCU, which process, and you get the beautiful images of your micron or nano object. Okay, now the main I won't go for the because main component electron gun. Why we need electron gun? Electron gun which produces highly energetic electron beam. How? Applying high tension with the tungsten filament. Okay, so due to thermionic emission, electron will be generated from the filament, and this filament will be attracted toward the or given path direction, downward directions. The anode is there below the filament. Why? Because positive potential you have to apply. The electron has a negative. So when you apply positive potential, this electron will be accelerated toward downward directions. Okay. So there are different kind of the electron guns. I will show you. Now the performance of microscope, it depends on the two parameters. One is the beam current, JB, or sorry, current density, that is JB, current divided by area. IB is a beam current, which is actually accessed from this aperture of the filament, well-met cells, which is called as. And second one is a beta. Beta is a 4I is a beam current. Now beam current, entering beam current from the aperture and outgoing aperture. Okay, so below anode there is aperture. I mean this particular cross-sectional angle. Okay, so now as I said, the performance of the electron gun is measured in current density, beam current. But you know that sometimes beam current is lost in the electron column, because this electron column, here I have shown you, this electron column, it's made up of element, metal element. So the maybe the loss of current. So therefore, it is not a good way to measure the performance of the electron gun by beam current. So it's always better to use brightness. How bright are your electron gun? Okay, so brightness is depends on this
brightness is depends on the entering and outgoing current. Now, there are different kind of the guns which is used, filament, tungsten filament, lanthanum hexaboride, and field emission guns. Okay, field emission guns. Now, lanthanum borohexide, it has a high brightness. So sometimes if you have SCM, it has a lanthanum hexaboride which gives a high brightness and the high performance, good performance. But disadvantage of this lanthanum hexaboride, because this is chemically reactive, so it's a moisture sensitive. So in order to use that gun, you need a ultra high vacuum. Suppose there is some kind of the moisture is remain in the chamber, your gun will be affect, or your filament, that lanthanum hexaboride will be affect. Okay, so this kind of the electron gun is expensive because you need ultra high vacuum system to maintain the quality of the gun. Okay, okay, so these are the some of the pictures of the electron guns. Electron guns is used just for the source of the light, highly energetic electron beam, and that highly energetic electron beam generated by the electron gun, we focus through the passes through the electromagnetic lenses to in order to focus on the smaller side, and we focus on that beam on the sample. Now you can see condenser and objective lenses are there. So if there is a low convergence, suppose the physical aperture here, you can get a larger spot. If the convergence is beam and the aperture size is bigger, that is high convergence, you get a smaller spot size. And the smaller the spot size you get the better the resolutions. Okay, so the operator should understand, if you have to get a better result, then you have to achieve as small as spot, or you can focus the beam spot as small as possible. Okay, now D3 is the equation for the beam spot. D0, M1, M2, M3. Now M1, M2, M3 is a magnification for the particular lenses. Depends on how many lenses you used, convergence lenses. M1, M2, M3. Okay, so D0 is the diameter of the beam, and D3 is the final diameter of the spot. Okay. So lastly, that last part of the SCM is the detector. Okay. Now the beam, here is your sample. The smaller the beam spot you focus with the help of objective lenses, you focus on the sample. So your sample will generate some signals. Okay. As for example, I can say when the light falls on any object, there are several physical phenomena takes place, right? Reflection, absorption of the light. Similarly, when highly energetic electron beam strike on your sample, there is a lot of signals are coming, different kind of the signals are coming. Similarly, light phenomena, light occur on the object. So electron beam strike on the sample, that we see. So that signals coming from the sample is detected by the detector, and the process by the system, computer software and all this, and then you get images, okay, black and white images or 3D images. All right. Hello, can you hear me?
Yes, sir.
Okay. So when beam, highly energetic beam that we see, electron beam generated by the electron gun, okay, that strike illuminated on your sample. So your sample has the different kind of the sample. So that beam is strike with your atoms, electron of the atoms. Then you get a different kind of the signals. That is, you get a Auger electron, characteristic X-ray, you get a cathodoluminescence effect, secondary electron, backscattered electron, continuous X-ray, because some of the X-rays are coming from the more deep of your sample. Okay, because of the collision, there are two types of the collision takes place, or maybe the scattering, inelastic scattering and elastic scattering. Some of the electron which having a higher energy, which will transmit it through your sample. Okay, because if it is a high energy, then In SEM, we actually consider two important signals, secondary electron and backscattered electron. Okay, so secondary electrons are detected, backscattered electrons are detected by detector, and the image will be processed. Okay, now secondary electrons are low energy electrons, which is kicked out from the specimen atoms by the highly energetic incident primary beam. Okay, and backscattered electron is nothing but which electrons, the primary electrons will collide on that electrons of the atom, and it will be backscattered, similar like you can say reflected, light reflected. Okay, so these are the most important signal. Now, okay, what is secondary electron? Maybe this is physics, you may can understand easily. When highly energetic electron beam strike on the sample, inner shell electrons is knockout, right? Suppose the K shell electrons here is knockout. So these are
Excuse me.
hello. Can you hear me?
Yes, sir.
Oh, I don't know what happened. Okay, let me share it again.
Okay, sir.
My screen is visible now.
Yes, sir.
Yes, sir.
So the most important signal in SEM is secondary electron, backscattered electron, and OZ electron. Okay. Now secondary electron is nothing but inner shell knock out the electron. For example, K shell electron beam, or we are bombarding on your sample. Backscattered electron just backscatter, colliding with the electron of your atoms of the electron of your sample. Secondary, sorry, OZ electrons is nothing but when we knock out the inner shell electron, that is secondary electron, the vacancy will be there. So how can say this electron, or you can say higher shell electrons will be a jump to the inner shell electrons, and there is an energy difference, right? That energy difference will be ejected in terms of the photons, and this energy is again knock out some loosely bonded electron, surface electron. That is nothing but we call as a auger electron, or you say OZ electron. So in SEM, backscattered electron is used for the contrast, and secondary electron used for, because the secondary electrons are coming from the inner shell orbit, it's carry information of your sample. Okay, and the secondary electron, it depends on the topography of your sample. So that is detected by detector, and the image is processed. Now backscattered electron, it depends on the intensity of the backscattered electron increases when the atomic number. Now your sample is a different atomic number. For example, if you take a copper nanoparticle, nickel nanoparticle, atomic size is different, right? So the backscattered electron coming from the different sample, the intensity will be different, which is depends on the atomic number. Second one is or you cannot say, or there is no increase in number of backscattered electron if we increase the accelerating voltage. So maybe the operator, you need to understand, or the scientists need to understand this phenomena, that if you even though increase the accelerating voltage, backscattered electron increases, no, there little changes but not effectively. Okay. Third one, backscattered electron emission, it depends on the tilt angle. Suppose you have sample, if you tilt it, then incoming electron will generate more backscattered electron. Okay, so these three things is important to understand the intensity of the backscattered electron, because backscattered electron is used for the contrast purpose. Okay, secondary electrons is very highly sensitive. As I said, it is highly sensitive to the topographical features. Okay, so how your surface orientation is look like, or see. So that's why the secondary electron detected, and because it is depends on the topographical features. Similarly to backscattered, there is no significant changes is observed if the intensity, not intensity, I mean the atomic number. Okay, so atomic number is different, then you don't see much difference in the intensity of the secondary electron. But in backscattered electron, you see it. Okay, and the production of the secondary electrons actually increases with the tilt angle, similar to the backscattered electron. So this is the important parameters for the secondary electron and backscattered electron. Depends on the tilt angle, depends on the atomic number. Okay, means atomic numbers also depends on the sample, I can say it. So another important parameter is the resolutions, because SEM has a high resolution power. Resolution means what? Now see these two objects. Okay, so if because second figure, you cannot say this is one object or two object, because you may say this object shape is like that. Okay, in first images you can say resolve, or second it is unresolved, because you cannot identify that is two, because two not separable distance, identify separable distance, or you cannot identify separation mark between the two objects. Okay, so in another figure you can say fully resolved, just resolved, and unresolved. Now here you can confirm, or you can say okay, there is a two object, but you cannot confirm, you can say just resolved. The third image, you cannot say these are the two spherical particles, right? Because you can, it's look like same single piece, single particle. But first you can say clearly two spherical objects are there. Okay, so well, the resolution of scanning electron microscope, it depends on the, as I said, beam spot. Okay, or the diameter of the electron beam spot you focus on your sample. Now ds is the beam diameter of the spot, which gives this equation A square bracket B IB divided by beta plus C divided by volt V 3 by 8 into C 1:4. Okay, now A and B is a constant, IB is a beam current, beta, I explained, beta is nothing but brightness of the electron beam, V is a applied voltage. Now C is a corrugation parameter for the optical lenses. Okay, each optical have you can say or you can say spherical aberrations. Okay, spherical aberrations in if you know the optical lenses, some of suppose you have the measure of the optical, you can understand the spherical aberrations. I'm not going to talk in detail about that. So in another equation you can express that resolution M is equal to SR divided by DS. DS as a beam spot, spot of the beam or diameter of the beam. Okay, SR is a screen resolution, M is a magnification. Okay, because SEM is meant to be a good resolution, and you need to understand what is the resolution. Okay, Next important parameter is called as a working distance. Okay, now working distance is nothing but the distance between the your specimen is nothing but your sample surface, and this is your aperture, objective aperture, this is your electron beam. Okay, so the distance between this aperture and specimen, it is called as a W or WD. You can vary this working distance. You can bring your sample towards the beam direction aperture, or you can pull down the direction using some mechanical tools are there. I mean, arrangement is there. You can vary that distance. Okay, so now the next important parameter, the depth of field. Depth of field. Now, are you able to see these images?
Yes, sir.
Can anybody tell me what difference do you observe in these two images? Okay, even first man is standing, a second man is also the same. But what do you see? In first images, you can see some background, right? He is standing behind. There are trees and the leaves. How can I say? Leaves falls on the ground, so you can see the background. But in second images, you cannot see the what is the background behind, right? So the depth of field is nothing but the point, the image appear to be focused below and above that images. Okay, so sometimes here you see the background as well. So that is called the depth of the camera. Okay, or you can say another one, the distance appear to be focused below and behind. Okay, suppose this is the focusing your point here. Okay, so this distance is called the depth of field, df, which is given by equation c divided by alpha m. M is a magnification, c is a constant, alpha is a divergence angles. Okay, now divergence angle, this is the divergence angle alpha. Okay, conical beam of your conical beam of half angle, that is divergence angle alpha, is equal to dA divided by 2 divided by WD. Now WD is a working distance. Okay, and D is the diameter of your beam spot. Okay, now angle alpha, and then change in angle, which is depends on the sorry, depth of field is depends on the divergence angle. Okay, so below is a why? Okay, below is a optical microscope images and scanning microscope images. Suppose some of the object, or you can say bacteria. Okay, now you can see optical microscope. You cannot able to see the features of, okay, or what is the background. This microscope, this object is sitting on what? Okay, but here you can see the behind that porous background, and this is bacteria, and detailed structure of that bacteria or object you can see, or you can say it is a 3D hollow object which has a needle. So resolution and the depth of field is more higher in SEM compared to the optical microscope. Okay, so I hope you understand the depth of field. What happened? Okay, so I just would like to show some of the images of the scanning electron microscope. See that this, you can say detailed feature on this, because the resolution power of the SEM is higher of the spider. This is, you can say, E. coli bacteria. It's maybe some of the bacteria we eat curd, right? So maybe if you see the curd below the microscope, you will be able to see such kind of the long bacteria, because our eyes, we cannot see this bacteria. Under the microscope, you can see this kind of the length and width of this bacteria. So more detailed feature, you can say. Oops, what happened? Okay, more images I can say. This is aluminum and palladium nanoparticles. You can see small. This is a 10 nanometer resolution. I mean the length scale down here. Working distance use 3.8. You can vary the working distance in SCM. Okay. More, we would like to show some of the image of our sample. This is aerogels. Now, from the first image, this is optical image. From that, you can see all the sample look the same, right? But the porous texture, you can see A, B, C, sorry, A, C, and F. F sample shows the more nanoporous structure. But in optical microscope, you cannot, or you are not able to see the nanopores or particles, right? So that is the beauty of the scanning electron microscope or the optical microscope. Okay, depends on your resolution. So these are the bits you can nanostructure, you can able to see using the scanning electron microscope. Now these are the more samples of the nanosphere which having the size 300 micrometer. Okay, now if you look this the features on the spheres, it look like a solid spheres, but if you focus more and more, you can see detailed features, right? From the low resolution, you are not able to see these petals or fibers on your nanospheres, right? But in scanning electron microscope, if you zoom it, go for the higher resolution using a lower working distance. Now here see working distance is used 4.2 mm. Okay, now the length scale is how much? From here to here is 300 nanometer. Now the one that sphere is 300 nanometer. Even that solid sphere, it has a beautiful structure. And that beautiful open pore, it has a size between the 10 to 50 micron. Okay, and this petal size, it's around you can say less than 10 nanometer. So now you can see this is the similar structure of the marigold flower. I think in Hindi we call it as a gendeka flower. So you know that you see this marigold flower, but this marigold flower structure is very larger, right? It is around 2-3 centimeter diameter. But these are the object nanosilica. We made it and we see under the microscope, and these petal size are how much? Less than 10 nanometer. But these petals of marigold, you can say the micron size, right? More than millimeter size. So that you can say nanomaterial, you can see the detailed feature using the scanning electron microscope. Even you see the custard apples, which is having size of less than 1 micrometer, you can able to see using the scanning microscope. Even rods, nano rods, you can able to see. Okay. So, hello. Kavita madam, hello.
Sir,
Can I take 10 minutes more or
Sir,
time?
sir.
Hello.
Yes, sir. You can take, sir.
10 minutes is okay?
yes, sir, you can take.
Okay, sure.
Yes,
Okay,
sir.
sir.
So, okay. Now we have talked about the scanning electron microscope. Now transmission electron microscope. Okay. Transmission means we see the images due to the transmitted electron. Before we talk about the secondary electron and backscattered electrons, we detect and we get images. Okay. So this, even we use the electron beam, electron gun as a electron beam source, highly energetic electron beam. Similarly, in TM we use, but instead of that, we use a high ultra thin sample. Okay, so images formed due to the interaction of the electron, transmitted electron through the specimen, and these images are magnified on the screen or using CCD camera. Okay. So study using a TM, you can see the, because below 25, below 50 nanometer object, it is very difficult to see under the scanning electron microscope, but you can see under the transmission electron microscope, because transmission electron microscope, as I said, is as a high resolutions. Okay. So bacteria, viruses are very smaller in scale. So even nanoparticles which having less than 50 nanometers, you can able to see by. So it has a wide applications in the biology, microbiology, forensic studies. Okay, in order to see the smaller object. Okay. Just to understand that transmission electron microscope work similar principle like a light microscope. Okay, scanning electron microscope little. It's not actual scanning electron microscope. It is a probing microscope. Okay, but light microscope, transmission electron microscope working principle is the same. Instead of only thing is light microscope, you use a light, and here you use a electron gun. Okay, so and instead of eye, here is a phosphorus screen user. There are also optical lenses in transmission electron microscope use electromagnetic lenses. Okay, so this you can say that. Now lambda depends on this equation 1.23 by V accelerating voltage. You can achieve the smaller wavelength, and smaller the wavelength, as we see in the equation, you can find the or get the smaller diameter, and smaller the diameter you get the high resolutions. Okay, I want to talk about the history of the TM again. This is the first TM I just see it. Let's compare the SEM and TM. Okay, in terms of the resolution powers. Now, types of the electron, which actually is called as the scattered or scanning electrons. In TM, as I said, transmitted electron beams. In SEM, you use 1 to 30 kV, but transmitted use high voltage, that is 60 to 300 kV, which is very, very large. Okay. Specimen thickness in SEM, you can use larger specimen thickness, but typically 150 nanometer size you can use in the TM, basic TM. I'm not talking about HRTM. Okay. In SEM, you get a 3D images, but in TM, you always get 2D images. Okay. Maximum magnifications, you get it 1 to 2 million times. In TM, you get 50 million times. That is 5 crore times. Then optical spatial resolution for the SEM, 0.5 nanometer. In TM, you get more than 50 picometers. Okay. So image formation is captured from the detector by secondary electron. Okay. And these are the TM, direct imaging of the fluorescent screen, PC, computer or CCD camera. So in SEM, actually, you don't need sample preparation, but in TM, you need some special look to or special preparation for your sample. Well, what you can get it from the TM? Crystal structure, crystal defects, second phase particles, nanoparticles, nanowires, nanorods. That morphology you can see it because it is in nanoscale. So that only you can able to see using a TM. Second phase particles like ILS. Okay, ILS is nothing but exactly similar to the EDX. Okay, some EDX feature is attached to the TM. Crystal defects, as I say, crystal defects means nothing is perfect, right? When you make the sample, your object, it has defect, stacking of the atoms. Like there are different kind of the defects in the crystals, stacking faults, grain boundaries, twins, dislocations, nature of stacking faults, that you can find out. Crystal structure means how that atoms are arranged. Okay, and that you can find out using a TM. Now, similarly, when the electron beam strike on your sample, you get different kind of the signal that we have talked. I'm not going to see. I mean, discuss about that because due to the time constraint. Imaging system, it is direct formation of the image transmitted electron beam. Okay. Simply to understand the TM, it's work like a projector screen, like a movie, what we see, because you have slide, instead of slide, you have thin sample. So light passes through the slide and the projected on the screen. Okay. Here in TM, that highly energetic beam generated from the specimen, which passes through the electromagnetic lenses through the aperture and focused on the fluorescent screen or CCD camera. Okay, just enlarge screen, enlarge images of your sample. Okay, these are the specimen. Actually, you use the special preparation on the sample grid. This is copper mesh. If you have copper sample, then use nickel grid. It's a tiny, I think 2 diameter of that circle mesh, and then you deposit your sample on this grid, and this grid you put on this sample holder, and this sample holder is insert. This sample holder also has objective apertures. Objective apertures means where you focus your beam in the smaller spot. Okay, so you can there are different kind of the aperture used, different size of the aperture, smaller to bigger. Okay, so depends on your resolutions or what you are looking, you can get it. Here I wanted to just tell you, though I am moving fast it because of the time. So you know, 4 important things you need to understand in the transmission electron microscope. One is a bright field image, means there are different kind of the operating modes. One is a bright field, second is dark field imaging mode, third one is lattice imaging mode, and the diffraction patterns. Okay, so bright field imaging, nothing but when electron beam passing through your sample, you have objective lens and you have objective aperture. Objective apertures is nothing but physical metal slit where you have small holes. Okay, so electron beam is passing through the objective aperture in such way that in transmitted electron beams are allowed to pass through the objective aperture, and diffracted beams from your specimen or sample are blocked, and then you get a bright field image. Okay, in diffracted dark field imaging means exactly opposite. Diffracted beam is allowed to pass through the aperture because objective aperture you are adjusted in such way that you block diffracted electron and you block transmitted electron and allowed to pass diffracted electron, and from that you get a dark field images. Okay, so in oppositely you can say in BF images, suppose you have sample, this is a metal nanoparticle, that sample is appeared in black color and background will be appear in bright in BF images. Okay, bright field images. In dark field images, your sample, maybe the metal nanoparticle suppose to be, it will appear as a bright and background it will appear as a dark. Okay, so this is the difference, whether what kind of the your sample is appear in your imaging modes. Okay, dark and field. You can see this is the silver nanoparticles. In this is a bright field image and dark field image. So silver nanoparticles on the carbon surface, that silver nanoparticle appears in the dark spot. Okay, in BF images, and DF images, this silver nanoparticles appears in a bright spots. Okay, okay, so bright field and dark field you understand. Now high resolution electron microscope is nothing but you allowed to pass both the electron, okay, diffracted and transmitted electron, and you get the pattern, means interference pattern. Okay, when you have transmitted electron beam and diffracted electron beam, they will depends on the phase difference, they will form the constructive or destructive interference pattern, and this due to that you will get the spot. Okay, either it is a black spot or white spot on the screen, and that's from the images. Okay, so that is nothing but high resolution images. Fourth one, what I said, 1 minute. Yeah, okay, so that is lattice images. It is called the high resolution lattice images, which actually normally you get it is in HRTEM. Okay, that you get it due to the interference of transmitted beam and diffracted beam. Okay, which will form the interference pattern. Diffraction patterns mean intermediate lengths adjusted in such way that sorry at the back focal plane of the objective lenses, that you get the diffraction pattern, or you can say SAD pattern. Normally it is called as a selected area diffraction patterns. Okay, now this is the example I wanted to show you here. The first you can say, first is the, you can say, single crystal. Okay, it has only one orientation. Second one is a, maybe the, it is a polycrystalline, but only it has a 1 2 3 crystals. Okay, three crystals, three single crystals, and you get this polycrystal. The C sample, it have many grains, means polycrystalline samples. Okay, so what do you get images in the transmission electron? Suppose you have single crystals, you get this kind of the patterns. Okay, you have many crystals, three crystals, then this, from the pattern from this crystal, this crystal, this crystal, then you get a more spot, more backscattered spot on the screen. If you have so many crystals, then you get the ring pattern. Okay, ring pattern. So this is for the single crystal, this is for the fuse. If you have amorphous sample, okay, amorphous sample, you always get the fuse ring patterns. Now you can see this is a few crystals, this is a many crystal, and this is a so many crystals, more crystal. Increasing grains, you will get the this white spot. You got it due to the interference pattern will be merged because there are so many spots, and then you get the ring patterns. Okay, so you can compare your pattern, and you can identify whether your sample is single crystals or polycrystals. Okay, so the one important parameter I just wanted to quickly say about it, selected area diffraction patterns, SAT patterns. Because suppose you have many polycrystal, but you want to focus on the one single grain. Okay, single grains. So single grains you focus means you have to select your objective aperture. You can focus in such way that you focus on only single crystals, and you get the lattice fringes. Okay, from the lattice fringes you can find out the crystal structures. Okay, I think I will skip that. Measure image contrast mechanism means you have to adjust the contrast in order to get good images. One is a mass thickness contrast, diffraction contrast, and phase contrast. Okay, maybe you can see in detail in the books. Maybe I will share the presentation if someone want. Lattice images, as I said, you focus on particular the grains, then you get the interference or images due to the interfacing, because you are not blocking. This is your objective aperture, and you adjust the back focal length at the intermediate length at back focal lengths of the objective lenses here, and you get the images. That is nothing but high resolution transmission images. You get it due to the interference of diffracted and transmitted electrons. So these are the HRTM images of Ni3Al. So you can see clearly this side and this side. You can see these fringes, right? Lattice fringes. So you can measure the distance between the lattice fringes. You get the lattice constant, and from the lattice constant you can find out the crystal structure. How? Using this, because this SAT pattern assumed to be as a reciprocal lattice. Okay, so real space lattice and reciprocal lattice, it is actually explained by the Ewald sphere. Now see, you get this beautiful pattern on the screen, right? Diffracted patterns. So you have electron beam. So you know the distance between the electron beam from your specimen sample and the screen. So that is called as a, suppose, L. Okay, L. Then you call this is Ewald sphere. So you know that Bragg's condition, 2D sine theta is equal to n lambda. N is an integer. Now you assume this is sphere, so you can know this distance from HKL to this by Ewald sphere. That is a 2 by lambda sine theta. Okay, so you can add this one. There is a using Pythagoras equation, you get the theta, and then you can, you know, this distance from here to here, this is actually 1 by lambda. Okay, so you can measure the distance L. Okay, suppose you get a pattern like this. So by equation R is equal to lambda L divided by D. Okay, so where D is a crystal spacing, d spacing, lambda wavelength. Wavelength, you know that whatever the electron beam you use for the what voltage, you know the wavelength. You can put the value of wavelength lambda. Okay. L, no, L is the distance between your screen and electron beam source, right here. I show here, this is L distance, your specimen, your film. So that is distance L, that is known, sorry, that is known. You can put the value here. Okay, lambda known, L is known, R is radius, means from the center spot to, suppose you assume this is 111 plane. Okay, so this distance you can measure R. So R lambda L, you get the value, you can get the D. So once you know the D, that is a crystal D spacing, you can find out the crystal structure. So using the SAD pattern, you can find out the crystal structures. Okay, so this is the HRTM. HRTM is nothing but you get more magnetic lenses are there, and high voltage is used instead of 150 kV. Use electron guns, high voltage around or more than 200 kV or 300 kV. And there is one additional intermediate lens is used in order to get the SAD patterns. So this is a Titan, which is actually very costly. When I was in Saudi Arabia coast, I used this. Normally, all equipped the TM is used with EELS, and it is cost around 55 crores. So it is very expensive because it has EDX, EELS, because you can find out the energy loss, how much energy loss from your sample, and from that energy loss you can find out the defect of your sample. So due to time, I skip this EELS technique, because you just observe the energy loss using the detector passing through your sample, and you get the different kind of the defects patterns. Okay, so you can oxidation state you can find out using EELS also. So this is the advanced technique actually. You can application of the TM, you can see, you can find out even in SEM, you cannot get the hollow sphere. Suppose this hollow sphere, just to want to advantage of the TM or HRTM. Now see, this is the SEM images and this is TM image. Now suppose I focus on this particle, so you cannot say maybe confirm that this particles is a solid or hollow. Okay, because backside you are not able to see. Now the TM, here you can see the contrast, right? So from that you can say, okay, this sphere also have this opening at the backside. Okay, so from that you can confirm my solid sphere has a hollow sphere, and which also have the back. So from that TM you can confirm, but SEM you cannot confirm that. So using tomography, you can see also. See, this is the nanotube, carbon nanotubes. You decorated with the palladium nanoparticles. Now, if you have to confirm that palladium nanoparticle you decorated on not only on the surface but in all directions. So you can see this particle B, you cannot able to see here, right? So you can say these particles are only on the front surface. And if you have to see, suppose some particles are situated on the back face of the nanotube, then you can take the TM images in 360 degrees Celsius, and then you can combine all together and you can make it the 3D images. Normally you cannot directly get 3D images by TM, but you can make it using a tomography, but it takes longer time. So I skip this. These are some of our samples using TM images. Beautiful. Before I show that marigold flower in the SEM, how it's look like 3D, but in TM, how it's look like. These fibers are very transparent. In core, you see it's not fibers is coming from the center also. Okay. So, but in SEM, we cannot confirm These fibers are only on the surface, or in the center is solid sphere. Okay, so you need a TM to see the advanced feature. Even just 2 minutes, I will like to show this tomographic images. This is solid sphere. We decorated some silicon nanospheres with palladium nanoparticles, which is very smaller, 2 nanometers, and we want to see this small black spot are all over the solid sphere, even inside the solid spheres of the silica. So loading up the nanoparticle on silica sphere, which having the particle size 200 nanometer scale, we can confirm it using a TM. So these are the TM images. More images you can see, detailed feature of the nanorods. Even these nanorods made of the small nanoparticles, which is less than 5 nanometers, you can able to see in the TM. Even pore size, which is actually less than 2-3 nanometers. This is MCM. You can see this white and black spot. So the uniform pore size you can see in TM, but you cannot able to see in the SCM. Even these palladium nanoparticles loaded on silica spheres, these black spots, you can able to see. These are the more images. Fringes, okay, lattice fringes. From that you can find out the D, and you can find out the crystal structures. So it has a limitations also. The sample, you need a very ultra thin, okay, you need ultra high voltage, ultra high vacuum, and TM cannot be taken as a colored images, even though so these are the some disadvantages of the TM, and TM is very expensive. So this is the TM which I used when I was in King Abdullah University of Science and Technology, KAUST, which actually cost 55 crore, because it has the ADX and yields and all the things. And you can have a lot more potential using these machines. You can see the pore, actually you can see the atoms also, okay, because it's a very high resolution transmission electron microscope. Titan, if you search in Google, it is one of the best TM HRTM in the world. Titan HRTM. Even you have corrected TM also, you can get biological TMs also, but this is very costly and very good TM. Maybe I don't think in Mumbai, maybe in IIT have or no, but maybe IIT is also, it's in basic TM, you might see. Anyway, so with that, I thank you, and I apologize taking too much time, and due to time I am unable to explain all the features of the TM. So thank you. Maybe you can have some questions, or maybe I can share my presentation. You can contact me through email or whatsoever. Thank you.
Thank you, sir. Thank you, sir. Very nice presentation, sir. Very informative, sir. Thank you, sir.
Thank you, madam.
Sir, more questions are there, sir. Now, we start with a few questions, sir.
Sir, how will you calculate particle size from SEM images?
Miss, how small you can see in SCM, right? Hello?
Yes, sir.
Yes, sir. Yes, sir.
How will you calculate particle size from SEM images?
Okay. Calculate the particle size in SCM image. Directly you can calculate, because there is a cursor. Now suppose, where is that images? Okay. Okay, let me open. Oh, this is a TM. Where is it? CMS.
Yes, sir.
Okay.
Yes, sir.
Yeah, can you able to see?
Yes, sir. Yes, sir.
Okay. Now this is the SCM images, right? So now below is the scale bar. There is a directly I can make the cursor here to here. I can make the line, and directly it gives on the TM operating software what is the size of that scale bar you drawn. Because this is solid sphere, I want to see the diameter. I can click here, and I can pull down the cursor down here like a Excel. This is the one method. But once you obtain the images, that you have to see in the machine, right? Another way, there is one software called as image software. Okay, you can download in Google image software. There is a 2-minute video image software in YouTube. You can easily you have to load your images, SEM images, and you can open this cursor and mark the line. You will show how much diameter of your particle. And also you can choose multiple particles, and they get average images also. You don't need to manually click it. You can apply something. There is a very good software, image software. Okay, you can download, you can use a computer. Maybe I can share the video later on also. But you can just type in Google image software, just 2-minute video. You will really understand how to calculate if you have SEM images with you. Okay. Hello.
So the next question. For the next question, sir.
Yes.
For liquid samples, shall we take TEM image is possible?
Now liquid sample, either you should have particles, right, dear? Now liquid means it's molecules. Okay, now molecules you have to see means liquid sample means your particle is in liquid, you mean? Hello.
Sir? Yes.
Yes, sir.
Only liquid, for example water. Now if suppose water you want to see, what you will see? Because it's water molecule, right? Nothing will see. So suppose your material is in liquid, but in TM grade you always take 1 drop of your liquid to put on your TM grade, and you dried it, and then you put it in your chamber, and then you will see. But if there is something, you will able to see. Liquid is nothing, you will see blank like white paper. Okay, if you have different kind of the molecules which having a size, actual size something, then you will be able to see the patterns. Okay, only liquid like a solvent, suppose you take a ethanol or acetone, you're not able to see. But you have the particle in ethanol, acetone, but you cannot directly insert the liquid here in the TM, because you need to analysis in ultra high vacuum. Obviously this liquid will be evaporate. Okay, so dried sample always you do it, putting on the TM grade. Okay.
Okay.
Next question, sir. What are the techniques to obtain uniform particle size without
this
agglomeration?
is the synthesis technique. Okay, so this is not characterized techniques, but agglomeration nanoparticle if you have to, then you need to some what do we call it, stabilizing agent like a formic acid or something like this. Suppose you want to synthesis nanoparticle uniformly you have to make it, then you need some stabilizing agent to add it for the synthesis process. And you mean the TM images? Okay, yes. I mean, okay, here. You mean like these images, uniform is particles are well dispersed, right?
Yes, sir.
So you can see, I observed very good images, because these particles not sitting ek ke upar baithe nahi, it's not sitting on the, these are uniformly images I observed. So for that, what you can do, you have to dilute your sample as much as you possible. Okay, very few amount of bottle, you take some ethanol and you take your powder, is nanoparticles, you put it in, sonicate it, and just take 1 drop. Don't take much drop on the to put in copper grid. If you take multiple drop, what will happen? You will ek ke upar ek, one after another nanoparticle are sitting, and then you cannot see well dispersed particles on the TM grade. Okay, if you have to see that, you can use very small amount of water, just 1 drop on the TM grade. Okay, because the preparation, as I said, preparation is very important for the TM sample. In SEM you don't need that much preparation. Okay. Yes.
Okay, so the last question, sir.
Your questions?
Yes, sir. Yes, sir. Thank you, sir.
Okay.
The last question, sir.
Yes.
Is it possible to see the presence of point defect using HRTEM? If so, we can calculate defect density.
Yes, you need actually very high resolution transmission image. For example, corrected images, corrected CCF we call as corrected cryo corrected TM. Because as I said, some advanced HRTMH you can able to see the what we said atoms, right? Now point defect is nothing but one single atom is missing, or maybe arranging some another atoms closely with the another close to the next to the atoms. That is a point defect. So single atom if you are able to see, that means you can able to see this where the point is missing, but you need to focus all over, or maybe where is the defect you have to I mean it's a lot more practice. You have to spend a lot of times on the transmission electron microscope to screen your samples. If you have a lot more point defects, maybe it is easy to identify, see on the screen, because what we don't see by eyes point that TM is able to see HRTM. So it is possible, I can say it, with very advanced HRTM, which having the resolution at the atomic scale. Okay.
Okay, sir.
Okay, sir. Thank you, sir.
Excuse me, ma'am.
Yes.
Ma'am?
Yes, ma'am.
Good evening, ma'am. It is a wonderful presentation. I want to convey one thing. Whenever I am touching the feedback link, it was going somewhere and I didn't fill the form. Yesterday also I faced the same issue. Today also I faced the same thing. I didn't get the feedback link now.
Ma'am, you
it's
mailed to
actually
our...
working, it's directing somewhere else, but it is working. I tried and I submitted now.
Hello, sir. Excuse me, sir. I didn't get it.
Yes, it's working, madam. Whenever we click the link and it directing to the some other page, but once again you have to click it, and now the feedback is open. I have filled it now. I tried it.
But when I am touching another screen, it is going to again in the same.
Okay, ma'am. Please, you ask the organizers. I tried now. I just
It is
filled
a
it.
problem in my network issue, I think.
Yes, ma'am. You mailed to our mail ID, ma'am. We will forward the feedback form, ma'am.
Okay, sir. Okay, ma'am. Thank you so much, ma'am.
Thank you.
Can I speak, ma'am?
Yes, ma'am.
Can I ask one question to Dr. Pradeep, sir?
Yes, ma'am. Please be louder,
Yes,
ma'am.
yes.
Sir, now is there any access for this Titan 10 in your university at present?
We don't have the Titan, but we have HRTM 300 kV. That is in the Nano
300
Center.
kV,
I am
sir?
in physics
Okay.
department, but that is we have a Nano Science and Nano Center department in the Mumbai University, and that is under maintenance. So maybe
Sir.
once it's repair, I will let you know. Okay, but currently that team is
Yes.
under repair.
Okay, sir. But you handle this in some another country, you said.
Yeah, Saudi
Okay,
Arabia,
sir.
King Abdullah University of Science and Technology.
Okay, then. So it's
That
too
Titan,
expensive.
I think,
So
I don't
even
think
for
it's
a
in Titan
sample.
Mumbai mein nahi. I don't have in Mumbai. I think in IIT also or TIFR also they don't have Titan, I guess, because it's very
Yes, sir.
costly. So maybe that they have 300
Yes, sir.
kV or 200 kV some API.
Yes, sir. That 200 kV time samples, if we they just charge very high amount for each sample, sir.
Yeah, 3,000
Even
around.
in
How much?
IITs. Yes, sir. Yes, sir. 3,000. After COVID, the charges are raised, sir. It's 4-5 for each sample.
No, but I think
So
we
it
have
is
in
very
NCL or maybe Shivaji University, they charge it 3,000 and some
Yes,
taxes.
sir.
Maybe 3,500
Yes,
it will
sir.
go.
Actually, we sent our samples to our Central University, Hyderabad, sir.
Okay.
It is very near to our location from Andhra Pradesh.
Okay.
That's why most probably we just sent a sample to the Central University, Hyderabad.
Yeah. I've been there. I think last 2 months ago I was there in Hyderabad Central. But I don't think charges will be all over the same TM. Maybe a
Yes,
little
yes,
bit
sir. Yes, sir.
500,000 difference.
After
That's it.
COVID, it raises, sir. Actually.
Yeah, because it
Yes,
takes
sir.
too much time and energy to
Yes,
some,
sir. Yes, sir.
and
And
one sample it takes long time.
yes, sir. They are providing number of images also. That is
Oh,
absolutely.
okay,
Yes, sir.
okay.
Thank you,
Yes,
ma'am.
sir.
Thank you, ma'am.
Thank you, ma'am. Thank you,
Thank
sir.
you, sir. So, formal conclusion.
Yes, yes.
A pleasant evening to all. I am very much happy to propose vote of thanks on this day. On behalf of our department, I express my deep gratitude to our today's resource person, Dr. Pradeep Sarvade, Assistant Professor, Department of Physics, University of Mumbai. Through your presentation, you elaborated about resolution of human eye, history and types of microscopes, SEM instrumentation, operating parameters, depth of field applications, about TEM, etc. We had an informative session, sir. Thank you so much, sir. Next, I would like to thank all the participants for their patient listening. Finally, I thank my colleagues for their support. Once again, I thank one and all present here. Thank you. So let's wind up the session, sir.
Thank you, sir.
Thank you, madam. Thank you. So
Thank
I
you,
can
sir.
log out, right?
Yes, sir. Yes, sir.
Okay, okay.
Thank you, sir. Thank you, sir.
Thank you so much, sir.
Thank you, ma'am.